we will be taking to IICHE and they will be preparing the final product at the site only. So where you will have a semi-cured product and it will be transferred to the end user part and their final product will be done. Next slide please. So this is very good slide, how to develop the cure kinetics as well as how to develop time, temperature, cure process window for a thermoset resin. So first you have to do, it is done using differential scanning calorimetry. I don't know how many of you know about differential calorimetry, doesn't matter. First thing is that you have to characterize in non-isothermal mode. So differential scanning calorimetry is nothing but you will be keeping a material inside a furnace where it is having closed environment. You apply the temperature, you will try to find out what will be the heat release or heat absorption profile of that material when I apply certain temperature. This is what you scan in the differential scanning calorimetry. So first you have to do the non-isothermal studies, which means that I'll be varying my temperature per time, like 10 degree per minute ramp or 20 degree per minute ramp will be used. So when I do that one, I can easily scan out. So it may be like room temperature to 200 degree, 300 degree. So that depend upon the thermal degradation temperature of the resin. So you can go until 300 degrees degree centigrade because most of the resin cure within this time frame, temperature frame. So when I apply the non-isothermal ramp, 10 degree centigrade per minute, so from 30 degree to 300 degree centigrade, you can clearly visualize when the resin curing getting initiated. Okay, so when the peak curing is happening, when the termination happening, you will have a peak. So from the non-isothermal study, so you will have the initiation point, peaking point and termination point. You have to select, so in industrial practices, we always cure the composite product at isothermal mode. Say for an example, 100 degree for 2 hours. We never make the product in non-isothermal mode. Why it is so? Any idea? Why non-isothermal mode is not good? So if I make some thick sectioned composite product, if I use a ramp, say non-isothermal mode of curing, so what will happen? What will be the temperature profile through thickness? It always varies, right? Because the fiber will have certain thermal resistances. So obviously you will have not the uniform temperature profile along the through thickness direction. So if the temperature profile is not uniform, the curing also will not be uniform. So if I'm having a quality product, I should cure the product at uniform curing, correct? So if you have a differential curing, the quality of the product will be differential. So due to that reason only, industrially it is practiced that you have to cure the resin part always with isothermal mode. Okay, so I have to select what is my isothermal temperature for curing. Okay, at least 3 temperatures I should identify. How can I identify? So what is my, from the non-isothermal study, so what is the onset temperature, onset of curing temperature, what is the cure peak temperature? In between I have to select 3 different temperatures which can be kept for prolonged time. So you have to keep the sample at the DSC and with the 3 different isothermal temperature with the prolonged time. So if they say that curing is for say 120 degrees centigrade, if it is for 2 hours, so I have to select like 100 degrees centigrade for 3 hours. So likewise, I have to keep it in the DSC and I have to find out the enthalpy versus time plot. What is the heat evolution behavior? That plot has to be produced. After obtaining that heat flow versus time plot, so as I told earlier, you have to find out degree of Q. So in classical chemical engineering kinetics, how you do the kinetics part? How we do the kinetics part? So if A reacts with B, gives you C. Very simple elementary reaction. So what we'll do? So degradation of concentration of any of the species, we will follow it up. From that we model this one. But in thermoset resins, you cannot do that way because since it is a pre-polymer, so the pre-polymers have different molecular weight and on site you will have different linkages happens. In an on spot, many molecules are getting engaged of different molecular weights. So that is not the usual way. The whatever classical way we follow, you cannot do it. Whereas we do the kinetics part in the indirect way from the heat evolution behavior of the resin. So since I say that this curing reaction is exothermic in reaction, you always have some heat is getting evolved from initiation to termination. So by scanning the heat evolution behavior, I can able to find out the curing kinetics. So the curing kinetics in terms of degree of cure, how fast the curing is getting progressed. So from this heat flow plot, so you know that it is heat flow versus time. So you have area under the peak, right? Total area is called total heat of reaction, right? Any instant of time, if I take partial area divided by total area, you will get the cure conversion alpha at the specific time. Next slide, please. Oh, sorry. So after getting degree of cure, what you have to do? You have to again differentiate that at every point. In the degree of cure versus time plot, you have to take slope at each plot, you will get rate of degree of cure. So you have a lot of classical cure kinetics modeling. So say for an example, nth order kinetics, you already get introduced with nth order kinetics, right? So next one is Kamal and Sarur model, cure kinetics model. Have you heard of Kamal and Sarur cure kinetics model earlier, which is called as autocatalytic model? So what is autocatalytic model? It doesn't need any extra catalyst, whereas the reaction itself catalyzes itself by the increase in the temperature due to heat evolution behavior, right? So you will get rate of cure as a function of time at different isothermal temperatures. From that you can able to model the cure kinetics. So you will get d alpha by dt as a function of alpha and t. So d alpha by dt is rate of cure, is a function of degree of cure and the temperature, isothermal temperature. So after doing that modeling, cure kinetics modeling, you will obtain with Arrhenius equation, right? So activation energy you will be getting, and you will get first of all K, okay, kinetic parameter. From the kinetic parameter with the Arrhenius relationship, you will get activation energy and frequency factor, right? So if the Arrhenius equation is lesser, the activation energy is lesser and the activation energy is larger. So what do you understand from that? If activation energy is lesser, it is very spontaneous reaction, right? So if the activation energy is more, the reaction is little difficult to happen. That is one thing. So what will the frequency factor? So do you understand? So you are from third year, second year. So reaction engineering is completed? No, not yet. Okay, fine, no problem. Anyways, so next one, next slide, please. So as I told, there are we have done it for different resin systems. This is one of vinyl ester epoxy resin system. So when I conducted the non-isothermal study, you can see that the cure onset is at 50 degrees centigrade. And the maximum heat flow is at 70 degrees centigrade. As I told earlier, I have selected 3 different temperatures between 50 and 70, which is 50, 60, 70, 3 different temperatures I have selected for doing the isothermal studies. Next one, please. So I conducted, so within 30 minutes, the complete reaction got completed. So you can understand as the curing temperature increases, the maximum heat flow increases. And when the temperature increases, time for the reaction decreases. Next one, please. So obviously, partial heat by total heat from the heat flow curve, I can obtain degree of cure. This is the degree of cure for 50 degrees centigrade, 60 degrees centigrade, and 70 degrees centigrade. Next one, please. So again, I have differentiated the curve, degree of cure curve, and I have obtained the rate of degree of cure curve. So for different temperatures. Next one, please. So these are different cure kinetics model. So you have the data for d alpha by dt, you have the data for alpha, you have data for temperature. You plot the you fit in all the kinetics model, because you cannot expect that this depend upon the nature of the resin. You cannot expect that every model will fit for all the resins. So you have to fit to the available models in the market, and you have to see which is qualitatively fitting and quantitatively fitting. Okay, next one, please. So this is for one of the model. So this is Kamal and Sarur model. You can able to see that it is somewhat closely met, but still we have to quantify this properly. Next one, please. So different Kamal and Sarur model it has been dealt with, like we have fitted. Next one. Next one. So these are different kinetics model with fit. So luckily what happened for this resin, most of the kinetics model what we were fitting was perfectly matching, which says that correlation coefficient is more than 0.99. So which says that it has a closer fit. But only thing is that you have to have a stability check. So previous slide, go to previous slide please. So here we have plotted d alpha by dt, that is rate of cure versus degree of cure versus alpha. So next one please. This model is fitting to this rate of cure versus degree of cure at different temperatures perfectly right. But next one, for stability check, I have to check whether the degree of cure versus time data also fitting or not. So when I do a cure kinetics modeling, d alpha by dt versus alpha plot also has to fit perfectly. Alpha versus time plot also has to fit perfectly. Then only I can say that this modeling is very perfect because the stabilization also had been checked. Next one please. So after getting this kinetic parameter K from the model, so I put into Arrhenius plot and we obtained the activation energy frequency factor. Obviously in any kinetics modeling, the two things expected, that is the Arrhenius, this is frequency factor as well as the activation energy. So next one please. So obviously we may obtain the kinetic parameters for higher temperatures, say 50 degree, 60 degree, 70 degree. I have only data how the resin cures at the studied temperature, right? But with the curing kinetics parameters, I can extrapolate to the lower temperature as well as more higher temperatures also, so that the complete cure profile of the resin can be obtained like time, temperature, cure process window. For that, I have to extrapolate the kinetic parameters. That's it. So next one, please. So this is for another resin. So this is for RTM6 resin, which is applied in aerospace industries. Whatever procedure I dealt you, that has been followed for same. It has been followed for the for this resin also. So you can see that non-isothermal cure DSC experiment, isothermal cure DSC experiment. Next one, please. So in this case, because to see the differences between the resins, earlier it was like curing temperature was 50, 60, 70, but in this case it is high temperature application resin, so you can able to see that it is 180 degree, 200 degree and all. So at the end you can see that, with the cure kinetics data, with a certain 3 or 4 experiments in the DSC only, I can able to completely obtain the cure profile of the resin. Okay, without any, because you cannot expect this data from the supply. Okay, right. So next one please. So now we will go for how to obtain the cure rheology. So when the resin is undergoing curing, the viscosity varies. Obviously you have to scan how the viscosity is getting varying during curing. So obviously isothermal DSC data, so just now we have seen. So we got the enthalpy data as a function of time and temperature for isothermal DSC experiments. That will give you degree of cure as a function of time at different isothermal temperatures. For rheology data, what you have to do, you take viscometer and you apply different temperature, say 50 degree, 60 degree, 70 degree. With the time, how the viscosity is varying, you have to obtain the data. From the any viscometer, you can obtain. Say, you can keep the sample at 50 degree centigrade, you just make the rotor to rotate in the viscometer and try to find out what will be the viscosity variation as a function of time. So from this, you can able to obtain viscosity as a function of time at different isothermal temperatures. So when you impose these two data, you can able to get viscosity as a function of temperature and the degree of cure. Next one, please. So this is like how we have performed isothermal viscosity temperature, isothermal measurements. So I kept it for 25 degree, 40 degree, 50 degree, 60 degrees temperatures, and you can able to understand that initially. So there is a reduction in the viscosity. When the curing started, the viscosity shoots up. So next one, please. So this is degree of cure. Earlier I have done the degree of cure for higher temperatures. So I can extrapolate the kinetic parameters and I can get degree of cure as a function of time at different isothermal temperatures, at lower temperatures also. So next one, please. So this is the superimposed plot, right? From the DSC experiment, I can get for different isothermal temperature, I can get degree of cure as a function of time. At different isothermal temperatures, I can get from the DSC data. And from the rheology data, I can get viscosity as a function of time and temperature from the rheological data. So when I impose these two things, I can relate viscosity as a function of degree of cure and the temperature. So you can able to see that at lower temperature viscosity remains constant for long period due to slow reaction before the attainment of resin gelation temperature. But at a higher temperature viscosity shows a biphasic nature. One is at lowering viscosity, the other one is shooting up viscosity. That's what it is called, biphasic in nature. Then it is applicable only until the gelation. So as I told earlier, the liquid viscosity undergoes first of all a gel state and a rigid solid state later on. Okay. So before, in industrial practices, we have to complete the mold filling within the 50% of gelation time. Okay. So because once the gelation obtains, the viscosity shoots up exponentially. And whatever model we are going to do, because this viscosity model is required only for mold filling, and the mold filling has to be completed within the 50% of gelation time. So if I can model the viscosity variation within 50% of gelation time, that's more than enough. That's what we are going to do. Next one, please. So this has been fitted, whatever data I have obtained, so rheological data. So with respect to degree of superimposed data, viscosity as function of degree of cure and temperature, that's simply fitted to certain equations, and this model is only applicable when degree of cure less than the degree of gelation. This is only up to gelation, the viscosity variation up to resin gelation. Next one, please. So next one is, like as I told earlier, so when resin undergoes curing, there will be exothermal heat. That exotherm behavior also is to be studied. Next one. So in this case, we have followed ASTM standard of D2471, and 100 ml of resin is taken, which is nothing but medium reactive isothermally unsaturated polyester resin, and we use curing aids such as accelerator and catalyst. Those curing aid proportion also to be fixed. Here we have varied accelerator volume from 0.5 to 2.5 ml per 100 ml of resin. So and cobalt octate is used as an accelerator in this case. Next one is catalyst volume varies from 0.5 to 2.5 ml, and we used MEKP, which is nothing but the methylethyl ketone peroxide. Per 100 ml of resin, it is varied from 0.5 to 2.5 ml. And for that, we have understood what is the exotherm behavior, like what will be the temperature, peak exotherm temperature, what will be the gel time, all these things will be had been studied already. So we have not used inhibitor. Inhibitor is a chemical which is to retard the curing reaction. So without inhibitor, because if I want to slow down the curing reaction, I can add some ml of inhibitor so that the curing time can be manipulated. Next one, please. So here you can able to understand the curing behavior. You can see that what we have notified what is the temperature hike during the exotherm behavior, during the heat evolution during curing of resin. So you can able to understand with higher MEKP, so there are lot more free radical supplier, because catalyst always supplies free radicals. So with that free radicals, more curing reaction happens, there will be temperature shoot up at the lesser time. Next one, please. So here we obtain gel time when the phase change is happening from liquid state to gel state, that we have notified. And you can see that when the catalyst proportion and accelerator proportion increases, decomposition of peroxide increases, which is nothing but the catalyst, and the crosslink get increased, because of that gel time decreases. So we have modeled gel time as a function of accelerator volume and catalyst volume. So next one, please. So peak exotherm, which is nothing but what will be the highest temperature that is happening during the curing of resin. So that also we have seen, and from this we can understand that peak exothermic temperature varies from 169 degrees centigrade to 145 degrees centigrade. For a particular accelerator proportion, lesser the catalyst proportion, the lower the peak exothermic temperature. What it says that if for a fixed accelerator proportion, if the catalyst proportion is lesser, say if I use 0.5 ml of catalyst only for a fixed accelerator proportion, I can see that the peak exothermic temperature is getting reduced. If I use more catalyst, obviously you will have high peak temperature during the curing. So again, peak exothermic temperature is also modeled as a function of temperature accelerator as well as the catalyst. Next one please. So again, the peak exotherm time. So we modeled peak exotherm temperature. We identified what was the maximum temperature uptime, and we also identified at what time this peak exotherm temperature is also obtained during curing. So that also modeled as a function of accelerator and catalyst volume percentages. Next one please. So rate of temperature rise, obviously you can get the slope of the temperature versus time plot, right? We have in the initial stage I have shown. So I have taken the derivative of each plot, and that is mentioned as rate of temperature rise. This is also one important parameter you should know when you study about curing of resin. Next one please. So next one is porosity and permeability. So in this case, permeability, as I told earlier, so resin flows through the porous media. The permeability is the physical permeability is the property of the fibrous media, which you have to know. So we have done it in a two different way. So I'll go faster. Next one please. Right. So this is one setup. This is using fluid conductivity measurement method. We are trying to find out the porosity. So this is nothing like we have a top and bottom mold. In the top mold, we used to have a electrical conductivity sensors. Okay, so in between the mold is the fiber mat is kept between the two mold. When the fluid is getting introduced at the center of the mold, when the fluid get expanded, like it flows through the media, when because the fluid is electrically conductive, right? So due to electrical conductance nature of the fluid, whenever it reaches any kind of sensor, the loop is getting closed and there will be flow of electricity. So I can able to obtain what is the time of reach of the resin through the fiber mat. Okay, so if for an example, this is at the free fixed radius, 1 centimeter, 2 centimeter radiuses, all the sensors are kept, right? Whenever the resin flow front reaches 1 centimeter, I can able to get the sensor will triggered on, I can get the time value. Okay, so I can get, and moreover at the injection port, it is injected at constant volume basis, and with the pressure transducer, I will be obtaining what is the injection pressure at every time. So I have pressure data, I have the flow front data like time of reach as well as the distance of reach. All these three data with the Darcy's equations, if I plot, I can get the that is permeability data. So this is the equation, P inlet is equal to Q mu 2 pi T phi K ln of R by R naught. So from this, only unknown is K. The phi is the porosity value. Porosity is obtained from the areal density of the mat. So next one please. So from this you can see that different test fluid is used. Okay. So different reinforcement mat is used. WRM is called O1 row 1 mat, and this is second one CSM is called chopped stand mat. This is different consistency for the mat material. So we have used different injection fluid like honey solution, glycerin solution, water and all, and we understand that with actually the permeability is the physical property of the fiber mat which should not differ with the test fluid used. But from the result we obtained was we got a different permeability for different liquid used. But the permeability is the property of the fiber mat. It should not ideally vary. So what the problem comes here is every fiber mat will have sizing. Sizing means some chemical will be coated over. So that chemical have preference towards any test fluid used. So in that case, you cannot use this permeability data. So we have to go for another way of measuring the permeability data. Next one is, so here we have obtained one other experimental method which accompanies the simulation also, where we use experiment as we have done it before, isothermal mold filling experiment. We use flow visualization technique. You record the flow with every time frame. I can understand where the reach of the flow front is. So that flow front as a function of time, flow front reach as a function of time, which is called as flow pattern. Experimental flow pattern is collected, and we used to do same conditions are getting mimicked in the simulation environment by varying the permeability value. Every permeability value I guessed, I collect a simulated flow pattern, I compare the experimental flow pattern and simulated flow pattern. Whatever the matched flow pattern from experimental and simulated, the guessed value, permeability value will be taken as effective permeability value. Next slide, please. So I have conducted the experiment as well as the same has been mimicked in the simulation environment also. I varied because it's a directional property, permeability at x direction, permeability at y direction. We have varied and we try to compare the flow front position at every time frame. So when it matched, I can understand that permeability at x y value, whatever matched value is taken as effective permeability value. So for this experimental setup, for a mold of 80 centimeter to 50 centimeter for unsaturated polyester resin and woven drawing mat of porosity 0.5 and injection pressure of 40 psi, I can get the permeability value of Kx is 2 into 10 power minus 10 meter square, Ky 5 into 10 power of minus 10 meter square, exactly matches between the experimental and the simulated flow fronts. Next one please. So it is also, and I worked out for different injection pressure also. I just wanted to see whether with respect to injection pressure, whether the permeability data is getting varied or not, but it is the same. Okay, you are getting the ideal permeability, which we can call it as effective permeability. Next one. So this is kind of comparison between different mats with a different pressure. So the shortcoming of the previous experimental setup is that you cannot use it for resins because resins are not electrically conductive. So this procedure what we have adopted can be used for resin or any kind of test fluids. Next one. So that's all. Like from the whole slides, so we can take home these things only. So we have developed Cure kinetics modeling for RTM6 resin as well as vinyl ester resin, and we have modeled that one using Kamal and Sarur autocatalytic kinetic model, and we have developed time temperature cure process window for both the resins, and cure viscosity also got modeled using rheological and DSA isothermal characterization data. And obviously we understood how to obtain the reinforcement permeabilities, reinforcement mat permeabilities using flow visualization technique. Next one please. So this is one small slide where I can project my lab. We are working on different aspects, right? So we have certain computational facility we have with COMSOL, as well as we developed newly one optimization algorithm which will avoid expensive simulations for composite industries. So we have developed one smaller toolkit which is very powerful. It can optimize, it can simulate any kind of environment. Only thing is that you should have COMSOL at your institute. That is one thing. So other than that, you can, and it can be used for any chemical process optimization also. So certain equipment facilities also. So notably we have 3D printers for different resin system, different composite system, even with nanofield systems also available. And there are lively, I have more than 1 crore rupee projects going on with the 2 industrial consultancy, one from state government consultancy and the other one is EcoBelief from Pune. So with this short introduction, I just close my presentation. I welcome you, sir, if there are any questions. So if you have any questions, I will be happy to address. So what I take, whether you understood everything or you didn't understand anything. Anyway, whatever, so yeah, any question please?
No, sir. Thank you.
Thank you so much. Thank you.
Thank you, sir, for sharing your immense knowledge with all of us. Now I request Dr. S.V.A.R. Shastri, sir, to present a memento to Raghuraj Pandya, sir. As we embark on this journey of enlightenment and discovery today, let us join together in extending our heartfelt appreciation and gratitude to Dr. B.K. Dubey sir for gracing us with his presence and wisdom. So now, may I request Dr. Brajesh Kumar Dubey sir to come over the dais to shed some light on plastic waste management, challenges and opportunities.
The introduction. So I'll go ahead and share my screen. I think you can hear me okay?
Yes.
Can you hear me?
Yes, sir. Yes.
Okay, good. So let me share my screen now. So let's start from. Okay, I think you can see my presentation now.
Yes, sir. It is visible.
Okay, so let's as I mentioned that on plastic waste management. So in terms of the topic that I'm going to focus on is on looking at challenges and innovative practices of plastic waste management in India. So what we are facing today and what are the challenges we have and what some of the innovative practices that our industry has taken up in this area, which needs to be possibly supported by different agencies and also replicated throughout the country. So that will really help us to control this situation of plastic waste, at least to some extent. So plastics, as we all know, as a material, it has done a lot of wonderful things. So plastic is a very versatile material. You can give numerous shapes and sizes to plastic. That's why you see lots of plastic products all around us, numerous shapes and sizes. It's essentially a synthetic or semi-synthetic organics. It's a high molecular mass. You can mold it in solid objects of numerous shapes and sizes. That's why it's very, very popular. So you see on the right hand side, you see all these pictures, all these products. Many of these products were actually not available even before plastic was invented. So many of these were not even there. So plastic has given us a lot of avenues. It has made our life quite comfortable as well. So I keep on saying that plastic actually as a material is a wonderful material. But what we have done is we have misused plastics a lot. We are using a lot of plastics, especially we are using a lot of single-use plastics. And we are just dumping it anywhere we want to just dump, on the side of the road, on the rivers, in our lakes, in our ponds, in our stormwater system, wherever we could, we have dumped this plastic. See, plastic never told us to put that plastic waste in different drains and other stuff. It's a mismanagement on human part. Like we are mismanaging plastic as a material and plastic waste, which is really creating the problem. So which I will try to highlight in first part of the presentation. It's a basic hydrocarbon structure. We do add a lot of colorants. You can see a variety of colors can be given, plasticizers to make it they could be molded into different shapes. There are stabilizers are used, fillers are used, which influence the properties of plastic. It's versatile, durable, non-degradable, and cheap to produce product. So that's the reason you see plastics everywhere. And part of it is also that we are lazy. Which we'll talk about that we don't want to carry our own shopping bags. We don't want to take our own containers with us. And then you end up using lots of single-use plastics. So there are different types of plastics. If you look at plastics and their recycling, starting from PET, HDPE, PVC, LDPE, PP, PS, and others. And you can see here, you don't have to worry too much about the details on here. So if you look at how much plastic waste is produced and mismanaged means not properly managed. So they produce much more plastic than us, but they are able to manage it in a much better way than we are doing it. So what we need to really work on having a proper plastic waste management infrastructure. See, we want to cut down on the use of plastic. We want to get rid of plastics, and those are all great. We have to. But plastic cannot be replaced unless you have a material which can do all the job that plastic does. and which is also has almost similar price. Unless it's economically is not replaceable to plastic, then you will have plastic, sir. So although we will just talk about that this ban, that ban, but still you will see plastics around just because there is no viable alternative. So our material scientists, our young engineers, our chemists, our chemical engineers, they need to really work on coming up with a material material scientists, which can replace plastic, do all the job that plastic does, and also at similar price, not too pricey. So then it can possibly, you can stop plastic and use something else. But whatever you will bring in, that also needs to be tested to evaluate it in terms of its long-term environmental impact. See, right now if you look at plastics, they came to save the trees, isn't it? That's how, if you look at the initial advertisements of plastics, it was that let's not cut down the trees, let's move from paper to plastic. That's how the packaging industry and everything will move to plastic. Now we are worried about plastics because we have actually totally messed up the plastic production in terms of too much of production and too much of usage of plastic, so much of single-use plastic. Nearly 40% of the plastic that we use today, we just use it once and just throw it away. 40%. That's a lot of plastics that we just use it only once and we just dump it into the environment. That's not actually that was not the intention of the people who invented plastic. They never thought that this is going to happen. But we humans have a tendency to always misuse the stuff. So, and that's what we have done to plastic too. So global plastic production, if you look at, the production is going to go up by 2050, as you can see in the projections. It's going to go up. We are hitting more than 1,000 million tons of plastic being produced by 2050. And out of that, in terms of what is happening to the plastics right now, it's incinerated around 1,000, the plastic that we have already produced, what has happened to it, accumulated plastic from 1950 to 2017, 9,200 million tons of plastic was produced between 1950 and 2017. Out of that, nearly 3,000 is still in use, 700 million was recycled, 1,000 million tons was burned, but 5,300 million tons is just discarded, and it has ultimately potentially made way to the ocean. And that's what you see, the highest ocean plastic polluters. India is quite high over there after Philippines. So it is estimated that 1 million metric tons of plastic waste enter the ocean every year, out of a total 67.5 million metric tons, which is there in the ocean right now. And this is the annual estimation in metric ton, how much metric ton of plastic is getting into the ocean from these countries and regions. Philippines leads the pack, and then we have the India also quite closer to that. So of course, some of these data we need to look at in what was the quality of data and all that, but we'll not worry too much for that right now. We can discuss it in Q&A. So global plastic production is kind of, again, packaging is which I told you earlier, mostly just one single-use, then building construction in terms of production and waste. You see the packaging waste. In terms of total plastic packaging that is made, nearly almost like 90% becomes waste very quickly. Building construction stays for a longer period of time. For other sectors also it becomes waste quite quickly. And then in terms of waste, you see LDPE more, you have PP, you have PP and fibers, HDPE, PET, polystyrene, and other categories there as well. So what happens to these plastics? They come from municipal sources, they come from industrial sources, they come from other sources, they get into land litter, microbeads, inland water litter, industrial leakages, marine litters, and finally they degrade, they fragment, and they become source of microplastics. So you see that in the environment from the variety of sources, ports and harbor, garbage dump sites, washing of clothes, tourism, shipping industry, fishing, recreation, sewage treatment plant. So from a variety of sources, plastic, using these pathways of stormwater runoff, river and streams, sewage discharge, tidal waste, industrial affluent, beach littering, they just make way and then finally reach to our, we start creating problem with the fish, Fish is, we see now pieces of plastic inside the fish. So that's a bit of concern. Many of us do like to have fish as a delicacy, but you don't want to eat plastic with that. Then riverine, estuarine, sea sediments, it goes to coastal surface water, beach sediments, so everywhere we are seeing traces of plastics now. So all these mismanaged plastics, they actually end up in the ocean. If you go on YouTube, you will find several videos out there of these plastics making way to the ocean. So when it goes to the ocean, because of the surface currents, what happens? This plastic breaks down. It breaks down, the smaller fish, they think that the plastic is actually the food, they eat that. Bigger fish eats, again, smaller plastics, or the smaller fish which has plastic inside their body. So that's why the bioaccumulation of plastic happens. And then we take the big fish, salmon and other stuff, and we try to enjoy the delicacy, but it may have plastics and plastic compounds in there, which we are not supposed to eat. It has led a lot of negative health impacts. And people are getting sick with variety of disease these days. Many types of disease are coming up, and many times we don't know why it is going, because we are exposed to many type of chemicals today in the environment, and plastics, microplastics are one of those. As you can see, Indian Ocean, North Pacific Ocean, South Pacific Ocean, South Atlantic, North Atlantic, and they are all called GYRE, G-Y-R-E. These are where the plastic is just in the surface current, plastic is just moving around, and that creates a huge amount of plastics. I think you can see on my screen now a ocean. On the left hand side, there are two videos running at a very slow speed, where you can see the person jumping into the ocean and see lots of plastics all around it. And this ocean the video has been taken not too far into the Pacific Ocean. So near Hawaii and those areas. So you see lots of plastic pieces all around. And this is what has happened because we have not managed the plastic waste properly. Had we had managed the plastic waste properly on the land, we would not see this kind of scenario. And so they are ending up in the ocean, and you will be surprised to know that what you are seeing in the picture is only 5%. What you are looking at the photographs here is only the 5% of the plastic. The remaining 95% is in the water column and in the sediments. So even if you do a plastic cleanup, even if you go for a cleanup of plastics, what you are cleaning up is only the top 5%. Remaining 95% will still be there, which is very difficult to clean up. So what we need to focus on is that plastic should not end up here. Isn't it? Plastic should not end up here. So how to do that? The number where we can plug, we have to put a plug, we have to put a stop gate in the land surface itself. And for that to happen, we need to have very good plastic waste management infrastructure. Unless you have a good plastic waste management infrastructure, things are not going to work out. Still, we will keep on seeing these kind of photographs, unfortunately, and at many places around the ocean. So we need to have proper waste management, proper plastic waste management. Ban is only on certain items. See, we have banned certain plastic bags, single-use plastics, but unfortunately, most of them are still available throughout the country. Although ban is there, but you can get it. It's throughout the country. You can get that. It's not. It's available. But then it's your. What we need to because even if you many of the single-use packaging stuff, your potato chips bag. Like if you go to the mall, you go to any store, Spencer type of a store or any store, you have dal, you have rice, you have sugar, you have salt, biscuits, everything is packaged in plastic. That is not banned, isn't it? You cannot really ban them also. So they will become they will end up here. So banning is only a part of the solution, a very, very small part of solution. We need to really have a very robust plastic waste management infrastructure if we really want to make a system better. What is doing it? It's making our marine ecosystem is getting, as you can probably see on the right hand side, a diver just going around, and he is As he's moving around the ocean, you can see lots of plastic pieces around him. Then entanglement, ingestion inside the fish, coral reef destruction, invasive species are developing on plastic bottles. So we see those. Many animal species have got entangled, and many species we see plastic pieces inside their body. And it is bioaccumulating, as I told you earlier, from a smaller species. From a smaller species, it goes to the middle level species. From the bigger species, and the bigger fish is caught by humans, it ends up inside the human body. In California and Indonesia, a study was done where they found that 1/4 of fish which was being sold in that market had at least some traces of plastic. In India, we don't do this study. Otherwise, I'm afraid that we'll probably find much more plastics than what they found over there. Otherwise, I'm sitting in West Bengal, where fish is a staple food. So nobody would like to know that we have plastic pieces inside the fish. Let us enjoy the fish. Don't worry about it. But see, if it's there, it's getting into our body. So decomposition, look at the marine debris in terms of they take long years. Banana peel, for a compressing purpose, banana peel takes only 4 weeks to degrade. Newspaper around 6 weeks if it gets proper atmosphere. Ropes 3 to 14 months, plywood, milk carton, as you look at the plastic bag, 10 to 20 years. Cigarette parts 10 to 12 years. Leather shoes 25 to 40 years. Then batteries, aluminum cans and all those lots and many years it takes. So then it has the effect on groundwater system, because this plastic marine debris, it has phthalates, PPTs, bisphenol A, PCBs, PAH, lead, nickel, and several other things are there, which when it gets into the water, these chemicals leaches into the water. Then it also becomes a mosquito breeding, clogging of sewers, mosquito breeding, eutrophication, urban flooding. See, we worry about that even with a little bit of rain, we see water flooded in many cities, maybe in your city of Kanpur as well. Maybe like we see that in Gurgaon, we see that in Noida, even in Delhi, Hotchkiss area, I have seen that in person. And also many cities. You just look at cities, you'll find that cities they have urban flooding happening. Why? Because the sewer is all fixed. All sewers are clogged with your stormwater system is all clogged with plastics. Where the water will go? It will be on the roads. It will get into the basements and other places and create problem. So not managing plastic properly, it creates a lot of other problems too. So why we should what is the negative impacts on health? If you look at the impact of plastic waste on human body, all these different compounds, it mimics estrogen, interface with testosterone, sperm motility, possible neurological disorder, carcinogen, development and reproductive toxicity. So as you can see, it kind of affects pretty much many parts of your body gets affected by plastics. And the bigger problem is the macroplastics getting into microplastics, becoming smaller pieces of plastic. So many persistent organic pollutants, they float and then they break down. And so there has been, and then become part of the microplastics. So it can be damaging to marine ecosystem, can lead to digestive blockage. And estimated annual microplastic particles consumed per person, 74,000 to 120,000. So that much of annual microplastic pieces are consumed per person in a year. So on person, say, if you just take an average, it's like 100,000. So me and you, everybody is taking, on an annual basis, on an yearly basis, we are getting 100,000 small, microplastic pieces getting into our body through different sources. So plastics from coming on the land and other sources, from the UV radiation, wave action, microbial degradation, it fragments, becomes microplastics, and then it also gets into the nanoplastics, it ingests by fish, human consumption there as consumers by aquatic animals, and even this plastic getting into our, nowadays you see that plastic in even the breast milk, plastic is there in placenta, so plastic in our blood, everywhere plastic is showing up, microplastics, especially micro and nanoplastics. So synthetic textile is one of the major source of microplastics. So as car tires, city dust, road markings, marine coatings, personal care products, and plastic pallets. So as with this we already mentioned about that you have this kind of food chain. Then also microplastics are showing up in the milk, drinking water, salt and sugar, fruit, vegetable, meat products, and seafood, and it does get into our body. There has been a study done on several brands of plastics, several brands of water around the world, and they found that on average 325 average number of plastic particles for every liter of water sold. So even the bottled water, which we feel like that it's a safe water to drink, but many of the bottled water have been found to contain plastic. It is not that only these brands have it, it is that these brands were tested. If you test other brands, you may probably find it there too. So there are a lot of scientists are working on microplastics' negative impact on health. Organisms are exposed to plastic in labs. Plastics have been detected into the environment under different species. There has been some studies where they say that how much microplastics are being consumed by babies by drinking that formula milk from plastic feed bottles in their first 12 months of their life. So UK suggests that average 3.1 million pieces a day. United States 2.5, Brazil is 1.8, global average is 1.6, so in India also something like that, it could be there. So if you think about all these things getting our body, of course it will have long-term negative impact. So microplastics, cellular damage, inflammation, oxidative stress, impaired metabolism, you have tissue translocation, digestive problems, development and growth, reproduction. So as you can see, a lot of mechanical toxicity, tissue organ system, physiological endpoints, those things are show up. So if you look at the overall plastic fate and all the fate and transport of different plastic sources. So it starts from many, like you get it from the transport aberrations of plastics from tires. You are looking at from leakage into the soil to waste sources. You have the wastewater treatment plant, illegal landfill, illegal dump sites, agricultural activity, fishing nets, your shipping containers. So a lot of, as you can see, from a variety of sources, plastic does make way into the ocean. And then it into the waters, and then it creates a problem. And then it's also a global warming climate change issue as well. We are, emissions from plastic, if you look at the life cycle of the plastic compared to a 500 megawatt coal-fired power plants operating today. So in terms of if you have how much plastics that we are producing right now, which if you say if you are closer to 2030 or 2019, so sometimes somewhere amount of the plastic industry is releasing more than 190 coal plants worth of emissions that comes out of 190 coal plants, and each coal plant is 500 megawatt. So whatever is the emissions coming from there, more than that is being emitted from this plastic production. And that leads to almost a lot of marine litters, almost 8 billion per year is the marine litter cost. Cost for fisheries, cost for aquaculture, cost for marine tourism and cleanups. There are 622 million annual loss in tourism. 81.7 million European Union fishing fleet annual losses that we have. So as you can see, lots of costs associated with being not managing the plastic properly. So what the system says, you of course try to, you know about, I think some of you any of the waste management stuff, we do talk about this inverted pyramid. This is like prevention and reduction first, then reuse, then mechanical recycling, chemical recycling, incineration, and then finally landfill. So if you go for mechanical recycling, feedstock, energy recovery, sanitary landfill, there are certain advantages and disadvantages, which like I'll be sharing these slides with the organizers so you can have those slides. I'm not going to read line by line here. So but for each one of those, there are some pros and cons. You do have chances of creating success from most, depending on the situation. Say if you look at if you have a market for recycled plastics, you can go for mechanical recycling. But if you don't have any plastic, any plant which needs plastic there, so then you can go for feedstock recycling. And if not, even if that's not there, you can burn the plastics and do energy recovery. So none of those things are possible. So based on that, stuff that we had looked at, if you can look at those in terms of some of the work that we have done recently. So this work was, which I'm going to very briefly talk to you about, is from plastic sea to source, sea searching solution to prevent plastic from reaching the ocean. So we were looking at how plastic is ending up into the ocean along, like getting in from through the river Ganges. So this work was done right before COVID, where we looked at how much plastic is getting into the river Ganges because of mismanagement of plastic waste along the way. So we had a kind of big work on that. So we started from all the way very close to Gomur. There is a place called Harsal. We started from Harsal and all the way we went up to the Bay of Bengal. And this was a National Geographic funded project. So our team was included people from India, of course, because we had to do it. So myself and two of my students, and then this is Jana Jembak, who is doing a lot of work in terms of plastics. We did actually a PhD together. She's senior to me by a couple of years in the PhD program. And then this was some of her students, and we had worked on basically to try to estimate how much plastic is getting into the river because of the mismanagement. So we looked at how much plastic is being produced, where the plastic is ending up, what is happening with the plastic, how much plastic they are able to recycle, how much plastic is they are not able to recycle, and what is happening to those, where they are ending up, and what are the pathway of it for leading to the river and finally to the ocean. So we talked to this junk shop and recyclables. We did how much littered plastic is there. So this is called a transect. In different cities we looked at. Transect is 1 meter by 1 meter, 3 feet by 3 feet. I think I have a picture here, yes. These are like 3 feet by 3 feet. So we would do it along the, at least you can see it over here. We will do it very close to the river. River is on the other side. And try to see how much plastic is there on the closer to the river, which will end up in river whenever there is rains and other stuff based on the topography and all. So we were trying to look at these plastic pieces and then try to identify what is in there. So total tracked item was 56,881. So these were the plastic food wrappers, tobacco sachets, plastic fragments, papers, and cigarettes. One thing we found was as we were closer to Uttarakhand and UP, we found mostly more of tobacco sachets, like Manish and Gutka and all that. And as or maybe Kesar, that Ajay Devgan one, I think Kesari, Jua Kesari or something. And then as you go down to Bengal and other Bengal and Bangladesh, you find more secret pieces. So you can also get some idea of people's what kind of things they consume. So this, you see all these numbers are actually average litter density per square meter. So that means how much littered pieces were there in a square kilometer as we were trying to look at in terms of how much plastic is being mismanaged. So the maximum one was actually in Chandpur, which is in Bangladesh, and the lowest one was also in Chandpur, which was in Rajbari. And in between, we saw that numbers kind of varying a lot throughout in different places in India. So these are some examples. So this is the transit data overall, like how much, and then size of the rectangle kind of tells you how much data points were there. And this is for one particular city. Where we were looking at the Sahibganj. We found around 6,320 items. So it was done along the river and in a certain area. We cannot do like it very extensive because otherwise you'll be just doing it in one city and we have to cover so many cities and we did it twice. So we had some representative numbers and based on that we tried to extrapolate for that particular city or town. So you can see these many plastic food wrappers, tobacco sachets, and seed-like plastic fragments and all that. Then similarly for Patna, these items. Then we also collected samples from drain falling into the river. So these are the drain just getting into the river. Ganges, as you can see the situation there. And again, lots of these states falling into the river. Collecting samples for that, looking at how much plastic is there and what type of plastic is there. And then along the process, we also found that while we are talking to the villagers, so when we are going along the way along the river Ganges, we also had a chance to interact with villagers. And some of the villagers actually told us that apparently they are seeing plastic pieces even in cow dung. In cow dung, they are able to see plastic pieces. So with the cows eating in the downsides, as you can see the picture over here, and these plastics over there, many times they eat this plastic, especially if it's a kurkure packet. For some reason, cows love that kurkure packet, and they would eat that. And then because it will get fragmented into the body, it does not digest, as you know, plastic just accumulates in the body, but it does get into a small, like a fragmented pieces, and those fragmented pieces are ending up in the cow dung. So we could see plastic pieces showing up in the cow dung, which was a concern, because see, if your plastic pieces are there in the cow dung, then the plastic chemicals, although we say that it does not get digested, but there will be some digestion, some sort of assimilation might be happening. So these plastic chemicals may get into our milk. So we don't want to have milk which has plastic chemicals in there. So this report is already there, available on National Geographic website. You can have a look at it. Another work which we did very quickly, I'll try to summarize in the next 5-7 minutes so that we have some time for question and answer. So it's plastic. This work was also done around COVID time. Started around COVID time, where we're looking at plastic as a key to addressing ocean pollution. This work was funded by there's a high-level panel for sustainable ocean economy, World Resource Institute UK. It was the 14 world leaders came together. So these are the leaders which were having some sort of connection with the ocean. Unfortunately, India was not part of that. But you can see all those different countries which were part of that, and it was our effort was being led by UN Secretary General's Special Envoy for the Ocean, Peter Thompson. So he was leading our team effort, and there were a lot of blue papers come out of this study. One of the blue paper which we were asked to do is looking at leveraging multi-target strategy to address plastic pollution in the context of already stressed ocean. So you can download this, or if you go to World Resource Institute website, you should be able to download that. And if you have any problem, let me know. I'll be more than happy to share the PDF with you. So this was written by 3 lead authors, myself along with Jenna Jembach and Miss Ellie Moss. As I mentioned to you earlier, Jenna, she is my senior from my PhD lab. She was a couple of years senior to me when we were doing PhD. And then Ellie is an independent consultant and researcher. But in other than these last 3, we had members from many places in the world, especially the countries which has ocean, which are touching the ocean. So we had global representation in terms of authors. So what we found, there are some key numbers which was based on the data collected. It's like a white paper to see that what is the present condition of plastics in the ocean. So 5 to 13 million metric ton of plastic go into the ocean each year based on different estimates. 1 dump truck of plastic per minute. So as we are talking, I'm talking for like an hour and 15 minutes, so that's 75 minutes. So 75 dump trucks, 75 garbage trucks of plastic getting into the ocean. While we are just discussing this topic today. This much, 13 billion per year in damage to marine environment. Only 3% of ocean plastic is floating. Some of the studies says 5%, so here I mentioned to you 5%. But this data that was collected here based on some estimates and all that, it was suggested that only 3% of ocean plastic is floating. Rest is all in the water column or in the sediments. So nearly 2 million microplastic per square meter on the ocean floor. So plastic is coming from all these different sources. Crop and animal agriculture, sewage treatment plant, industry, vehicle wear and tear, from the solid waste, we see all those, and then also a lot of things happening within the ocean as well. So plastic is getting there. Municipal sources, agricultural, aquacultural sources, industrial sources, maritime sources. And you have microplastics, macroplastics, but there are other solid waste as well. Nutrients, pesticides, antibiotics, heavy metals, oil and gas, all those things are making into plastic, into ocean. But why? See, we need to have healthy ocean economy. Ocean needs to be healthy, otherwise it is going to impact us as well. It will impact very negatively to the planet. So ocean, we already kind of talked about the species and all that. Health issues, reproductive, developmental, neurological, endocrine problem, immunologic problem, adverse health effect from chemicals, acute or chronic toxicity, increased exposure to pathogens or mosquito-borne disease, and it is impacting the economy in a very negative way. Its economy is getting impacted in a very negative way because of this. So what is the solution? The solution that was proposed is improve the wastewater treatment, improve stormwater management, go for green chemistry practices or new materials, try to practice radical resource, recover, recycle, improve the coastal zones and all that. So summary of intervention and pollutions addressed across different sectors and sustainable development goals, that was also summarized as part of this white paper. It's essentially around 60 to 70 pages report, which is there, talking about different types of pollutants, different SDG numbers, different types of pollutants, and what can be targeted and how to make it happen in terms of different interventions that is listed over there. So if you're interested, you can always go to this oceanpanel.org and look for this white blue paper, and then you will get that. So in terms of what is happening, so we talked about plastics, the problem with plastics, we talked about some of the health effects of plastics. We also talked about what is some of the research projects, some of the research initiatives that is being done on plastics. Very briefly, we touched on that for the interest of time. Some of only two work that we are doing in our lab, I tried to highlight. We are doing some more work in this area. Probably we can talk about that if you in Q&A or sometimes later. So there are how the plastics, what are the initiatives from the government side, from the industry side to manage the plastic. So local government and local government departments, they make up the public sector at the city level. So there are large and small registered firms in terms of private formal sector. We have the waste pickers, dump pickers, waste purchaser, merchants. So there is an informal private sector. Then the collaboration can take the form of public-private, public-community, public-private community, and then try to come up with some solutions. So there are some initiatives that are going on, for example, Prakriti, which is absolute prohibition of single-use plastic, such as earphones with plastic sacks, plastic flags, plates, glasses, and all that as well. So co-processing of plastic waste, one of the things that government is proposing is let's try to use this plastic as a fuel. So co-processing of plastic waste in cement clean. But even for this to happen, you need to keep the plastic clean. If plastic is very dirty, none of the cement plants will actually take it to use it. So co-processing indicates substitution of primary fuel. So one of the advantages is that you can use the existing facility, but then you need to make sure that you collect properly and then you keep it clean as much as possible. Others, people are using plastic waste in road construction. Again, that same thing here. Advantage, you need to make sure that it is clean. Unless it's other plastic waste is collected, it's clean and dried. Then shredding of plastic waste, then you have this aggregates, shredded polymer waste is added to the heat stone. So basically, plastic here is replacing the bitumen. So in place of bitumen, you are using plastic in there. And plasma pyrolysis technology is also being used in some places, but it's highly energy intensive, so you need to be careful. Usually for biomedical waste, which has plastics in them, this could be employed. But traditionally, municipal solid waste, it seems to be a bit on the higher side in terms of price. So plastic has been used as a paver blocks in Hyderabad and some other territories too. There are some startups which are actually working on plastic paver blocks. Plastic bottles have been used to make textile, to like the newer t-shirts and all that. It's made out of PET bottles. Especially those IPL is going to start, I think, today or tomorrow. You see those IPL signee t-shirts. Many of those t-shirts are recycled plastic. And even our Prime Minister of India wore a light blue colored jacket a few months back, which was made out of recycled plastic. So there are Bangalore, they're making the road. Kolkata, Salt Lake, Puja says no to plastic, plan to reuse pandal decorations every year. Kolkata Municipal Corporation also takes recycled plastic to use in the road construction. And it's also in Jamshedpur, and Chennai was the first city to do that. And then there are others there too. So in terms of plastic to fuel is also being tried, and it's a research at Indian Institute of Petroleum, Dehradun. They had some research done over there. But it never really took off. It's because it's again economics was not working out. So government is still trying to see if it can be revived. So then people are making bricks out of plastics, where plastics and other waste stream. They're trying to build bricks which could be used in different applications. There are, plastics are converted dirty as plastic waste into recycled granules. So making recycled granules for flexible packaging, automatic covers, and all those kind of stuff. Then this is a new a startup, I think more than a year or two now, IICHE, which makes a fabric that feels like leather, but actually it is coming from single-use plastics. So they say that don't just do it right. So they are trying to use recycled plastic bottles and shoelaces, recycled rubber, and recycled plastic bags, and then you come up with shoes, which the shoe actually cost around 5,000 rupees though. That's what I heard. I haven't checked out the price. Around something 5,000 or maybe slightly below than that. So innovative approach, people are using these tires and other stuff for playgrounds and all those stuff as well. So let's say another approach is there. There is a multi-layer packaging is a big problem. So here just try to collect the multi-layer packaging and do this resource recovery, recycling in terms of different polymer types and all that. That is also people are working on. Lots of startups actually coming up and doing some work. Banyan Nation is one of India's first vertically integrated plastic recycling company. So it uses its technology to integrate thousands of informal workers into the supply chain and produce premium quality plastic, polyfilm plastics, so for mainstream and high quality applications. So that's also being done. So thank you. I think that was the presentation I had. We started at 3:40. So yes, I think we have some time for question. At least 8 to 10 minutes we can take questions if that's okay. So I'll just stop sharing my screen. And then this is my number. This is the number has WhatsApp as well. Later on also you can get in touch with me if you want to, if you need to. You are more than welcome to do that. And you can find my contact online anyway, if you just go on IIT Kharagpur website. So let's stop presenting, and if you have any questions. I know it's kind of difficult after lunch. I'm sure you must be having a very good lunch, which I missed at HBTI and during the conference. The lunch के बाद ऐसे ही थोड़ा आदमी सुस्त हो जाता है, but still if you have, let me know your questions. Can you hear me?
Yes, sir. Yes, sir. Yes.
Yeah. So, is there any questions? If not, then If not, then you can excuse me. Then I'll just sign off. Okay, it looks like no questions. So maybe either it was very clear or it wasn't clear at all. Only on those two chances you will have no question, when you understood it 100% or you did not understand at all. So that's okay.
Yeah, Professor Vijesh.
Yeah.
Yeah, this is Professor Anil Verma from Department of Chemical Engineering, IIT Delhi. So after your presentation, I have to present.
Okay.
So I'll appreciate the way you have presented. It was very clear, at least to me, and I learned a lot. So thank you very much for the presentation. Nice presentation. Okay.
Thank you, sir. Thank you. So next time I'm in IIT Delhi, I'll try to meet you.
Yes, definitely.
मैं क्या रहता हूँ तो मॉर्निंग वॉक पे जरूर जाता हूँ आपके वो स्टेडियम में. Okay then. You go ahead.
Once again, I would like to thank Dr. Brajesh Kumar Dubey sir to share his knowledge on plastic waste management. Now, as we move forward, it is with great honor and pleasure that we welcome Professor Anil Verma sir to our event today. So now, may I request Professor Anil Verma sir to shed some light on an overview of EV and role of chemical engineers.
Sir, your mic.
Okay. Thank you very much. Yeah, so thank you very much for giving me the opportunity to discuss about EV and the role of chemical engineers. So I understand that at this moment it is difficult for you to concentrate on the talk because after the lunch, as Professor Brillis told, after the lunch it is very difficult to be concentrated for a longer time. So I will try to make the things more simpler. So what I'll do in order to save the bandwidth, I'll close my video and I'll share the slide. Is it all right?
Yes, sir. Yes, sir.
So I hope the slides are visible and I am audible, right? Can anybody confirm? Can anybody confirm if I am audible and my slides are visible?
Yes, sir. Yes, sir.
Okay, thank you very much. So first of all, I would like to thank Professor Shastri and the entire chemical department and HBTU for giving me the opportunity to interact. I generally do not like to deliver the presentation online because I don't feel good because I cannot see the audience and today even you cannot see me. So the topic of the presentation is an overview of electric vehicle and the role of chemical engineers. So with the world's largest population and an economy that is expected to be, say, worth around 7 trillion by 2030, India's growth potential is substantial, and this will inevitably lead to increase in country's demand for the resources and its environmental footprint. So primary energy demand, if you see, it is around 441 MTOE to 775 MTOE given by various agencies, and we are expecting that the demand for the primary energy will go from 1,250 to 1,500 MTOE by 2030. We are also aware that we are the third in the crude oil consumption and we are 20th in production, right? So transport sector, if I talk about the transport sector, because I have to concentrate on the electric vehicle and related things. So the transport sector, if you see, the 18% of the total energy consumption, whatever we have is because of the transport sector, and it is responsible for 13.5% of CO2 emission. And out of that, this 90% road transport segment alone, 4% is by the rail, 4% is aviation, and remaining 2% is for the miscellaneous. So because of the CO2 emission, there is an increasing concern of the global warming, and the indicators are known to everybody that the climate is changing and rising sea levels, worry of coastal cities, frequent natural disasters, early hatching of eggs, and many more. So what I will try to do, I will try to talk about first the ICE vehicle that we are using. So almost everything, therefore I have written those statements, almost everything which is going into and coming out of the ICE vehicle is toxic. So if you see the internal combustion engine, so it generates the waste heat, it generates the toxic air pollution gases, generates the greenhouse gases, dependency on the foreign oil, it also generates a toxic solid waste, requires a toxic fuel and fluid to operate, for example, for the coolant and all. So one important thing I have written over here, ICE, internal combustion engine, is the highest evolution till date. So this technology is at the highest, at the peak of its evolution, right? But at the same time, if you see, it is the most inefficient device on the planet, right? Why I'm saying it is the most inefficient device on the planet, although it is the most evolved technology, one of the most evolved technologies, because whatever combustion we are having, only 20% of that combustion is converted into the mechanical energy. Rest is going into the heat lost, right? And out of that 20% combustion energy that we are getting, one third is used for the aerodynamic drag, one third is used for the rolling, and one third is used for the acceleration. So you can understand that it is the most inefficient, though it is highly evolved, right? Now, because of the CO2 emission and all those things, India is also committing, or in fact, it has committed in COP26 and further, that the 5 points plan that we have is 500 gigawatt of non-fossil power by 2033. So these are the commitments India has done. So 500 gigawatt non-fossil power, 50% electricity from the renewable by 2030. Net CO2 emission should be down by 1 billion metric ton by 2030, and the carbon intensity reduction by 45% by 2030. That is with reference to the 2005 data. And we have also committed that by 2070, we will be net zero carbon emission country, right? So other developed countries, they have committed that by 2050 they will be net zero. Okay, to achieve the efficiency and the emission goals that have been set by the national and the international agreements. So it does not, at the same time, it does not improve the diversity of the energy sources. So if you see, the long-term strategy can be the electric vehicle, which can be charged initially by the grid. Later, you can think that if it is charged by the renewable energy, that will be the best option. So presently what we are doing, we are taking the electric vehicle and we are charging with the help of the grid. And that grid is primarily run by the coal power plants. But ultimately we have to reach to charging by the renewable energy. Now just let us see what are the different classification of the electric vehicle. So there are a few terms I have shown over here. First is the HEV. HEV means hybrid electric vehicle. PHEV means plug-in hybrid electric vehicle. BEV is the battery electric vehicle. FCEV is the fuel cell electric vehicle. And SEV is the solar electric vehicle. Okay, so these are the different terminologies that we have. And if I wanted to segregate these, or if I wanted to give more detail about this classification in terms of the energy and the power sources, then you can just see, if I write the type of vehicle over here, energy sources, and how it is how the propulsion is done. If I just divide these three things, we can understand the traditional vehicle, which is the IC engine, the source of the energy is either gasoline or the diesel or CNG. Okay, and who is who is giving the power or who is propulsing the vehicle, it is the combustion engine or the ICE, internal combustion engine. So this is the traditional vehicle. So in traditional vehicle, the energy is the gasoline and propulsion is by the engine. If I talk about the hybrid electric vehicle, the propulsion is by HEV is same, only the P or the plug-in is written over there. That means you have the energy source is the same, gasoline or the diesel, but additionally you have one onboard battery charger. That means you can use it, you just plug in into the wall socket and you can get the energy to the grid. And propulsion is again, it is the combination of both combustion engine and the electric motor. If you talk about the battery electric vehicle, which is the BEV, so in this particular case, only electricity is the energy source which is stored in the battery. So battery we have to use as an energy source and we can run the vehicle, and the propulsion is by the electric motor only. Please see there, in these two cases, combustion engine and electric motor both are there. However, in case of battery electric vehicle, only electric motor is there. If you talk about the fuel cell electric vehicle, energy source is through the hydrogen gas and the propulsion is the electric motor, using the electric motor. Similarly, solar electric vehicle SEV, the energy source is the panels through so solar energy falls onto this panel, and from that panel we get the electricity. So that electricity is used to run the motor and we drive the vehicle. So this is based on the energy and power sources, how we classify the different electric vehicle. There is another classification which says by the degree of hybridization. So out of these, if you talk about the hybrid electric vehicle, these can further be divided into the 4 parts. Again, these are not the set standard. See, these classifications are not standardized. This is based on whatever is being practiced. So the degree of hybridization is there are 2 technologies that we are hybridizing. So how much hybridization we are doing, based on that we are giving the name. For example, it can be micro hybrid electric vehicle, it can be mild hybrid electric vehicle, it can be full, or sometimes we say strong. So full is not a very good name, but people use it, therefore I have written. Otherwise we say the strong hybrid electric vehicle or the plug-in hybrid electric vehicle. The difference in these 4 degree of hybridization you can understand by the names, but I'll just tell. In this micro HEV, the ISG is there, okay, which is a start-stop function, integrated starter generator. ISG is the integrated starter generator, which helps to start and stop, and it also has the ISG, which can power assist. One function is only once your vehicle is stopped, then you are just taking away the foot from the brake pedal. What may happen? The energy will come from the battery and your engine will start. Okay. So in that way you store or you basically save a lot of energy. In case of ISG power assist, not only the start and stop function, but it will also have the power assist. It will give you some assist in the power. Therefore, these 2 are the important part in case of micro. And in these 2 technologies, in these 2 particular technologies, if it is utilized, then the efficiency improvement is around 3 to 10%. Okay, and it is used with the conventional engine. Engine size is almost same, but you have a motor and additional battery which can store the brake energy and which can be so that the battery can be charged. It can be for the start-stop purpose or it can be for the power assist purpose. So the electric power which comes from the motor is roughly 2 to 5 kilowatt. So the size of the motor is not very high. For example, Maruti Ciaz, Honda Civic, and there are many, nowadays almost all the vehicles, most of the vehicles are micro hybrid vehicles. Next is the mild hybrid electric vehicle. So whatever is we have discussed in the micro, we have some additional energy and the power, then we say it is a mild hybrid electric vehicle, and the efficiency improvement is around 15 to 20%. The size of the engine, which is the IC engine, is almost same. But as we have seen that additional power we can get and additional energy we can get under the mild HEV. That means the power that we can draw from the battery or we can utilize through the motor is around 3 to 10 kilowatts. So the motor size is increased. At the same time, number of set of batteries are also increased. For example, Honda Civic is having that function. Next is the full or the strong hybrid electric vehicle. Whatever we have seen in the mild, right? We have additional energy and the power, and the efficiency improvement is around 20 to 30%. However, in this case, because now you see slowly what we are doing, if we are going from left to right, the size of the battery is increasing, size of the motor is increasing. If both things are increasing, then we have to accommodate in the available space. So what we have to do, we have to downsize the engine. Okay, so the engine size reduces and the motor and the battery content increases. Here in this case, the electric power is around 10 to 20 kilowatt, and there are many examples: Toyota Prius, Toyota Camry, Kia Optima, Maruti Grand Vitara, and so on. The fourth one is the PHEV, which is the plug-in hybrid electric vehicle. So it is the same, whatever we have seen over there, full HEV, plus additional energy and power. That means we have further more powerful electrical components, for example, the motor, and more number of batteries can be there. Apart from that, we have the external charger also. That means if we are not able to charge our batteries with the help of the engine, it can be charged with the help of the external charger also, right? So in all these previous cases, you can see whatever charging of the battery is done, the charging of the battery is either at least from the regenerative braking, and it is because the engine is running and it is powering and giving the power to the battery so that the battery can be charged. Now there is classification based on the arrangement of the powertrain. So it can be series arrangement or it can be parallel arrangement. So examples are given: BMW i3 or parallel arrangement of the powertrain. Powertrain means if it is ICE and motor, how they are connected, right? So for example, Honda Civic, there is a term which is known as the degree of hybridization, means how much hybridization we are doing. So degree of hybridization is defined as the ratio of the power from the electric motor divided by the total power from both the technology, which is one is the IC and other is the electric motor. So degree of hybridization, if it is 0, that means we will say it is pure IC based engine. If I am saying the degree of hybridization is 1, that means we are saying that it is the pure electric vehicle or it is a BEV. Otherwise, 0 to 1, in between it is either mild, micro, strong or the PHEV. Now, if I just see how a battery vehicle or the battery electric vehicle looks like, so it has very fewer components as compared to the IC engine. So primarily a big battery bank is there. We have the motor controller, and motor controller is used to drive the vehicle and control the vehicle. We can have the plug so that we can charge it from the socket. If I just give you some detail of the present vehicles, so 4 vehicles I have taken. One is the Hyundai Kona Electric, another is the Tata Tigor, MG ZS and the Mahindra E20 Plus. Now if I talk in terms of the energy capacity, charging time, range and typical price, you can see the energy capacity of the Hyundai Kona is around 40 kilowatt hour. Now this 40 kilowatt hour is primarily the energy that we are containing in the battery. So basically it is the size of the battery. So it is the size of the battery in terms of the kilowatt hour. Now, if I see the range is roughly 450 kilometer it can go. Price is 24 lakh rupees. Tata Tigor, 21 kilowatt hour or the 21 unit of the electricity the battery contains, and range is roughly 200 kilometer and costs around 10 lakh rupees. Similarly, the MG around 45 kilowatt hour, 340 kilometer, and the ex-showroom price of Delhi is 24 lakh rupees. Similarly, for the Mahindra, 15 kilowatt hour, 140 kilometer, and 6 lakh rupees. So here, if you see very carefully these two data, then you can have a thumb rule that 1 kilowatt hour of the energy can give me roughly 10 kilometer of the run. Right? Similarly, if you see here, around 20 kilowatt hour of the energy, you can go roughly 200 kilometer. That means 1 kilowatt hour of the energy can give you 10 kilometer of the run typically. Okay, so this number you just take care in your mind. Later I discuss this further. Now EVs are becoming increasingly important. That everybody knows because of the various reasons which everybody knows. Therefore, I will not discuss that. What I will discuss, one of the concerns. Okay, one of the concerns that is important that we will see. So if we have to charge, generally what we do, we charge the electric vehicle by using the power socket in our home, or maybe in the charging station we can charge, right? In the previous case, you can, so I did not discuss, but in the previous case, you can see that how much time it is taking. So if I use the AC wall, roughly 6 hours, this is around 12 hours, this is around 6 to 8 hours, this is around 7 hours. If I use the DC fast, then maybe 1 hour, or DC portable maybe 20 hours. So you can see why we are taking this much time in order to charge the vehicle. So if we buy electric vehicle, if I using the socket which is in my house, then it will take 6 to 10 hours. Why it is taking 6 to 10 hours? What are the issues that we in a traditional car? You may take typically 2 minutes. In 2 minutes, your full tank will be full, right? So if you want a similar time of charging in case of electric car, how much power do you need? So very simple calculation. Energy in 2 minutes. Okay, so 2 by 60 R, right? So R will be cancelled. You will see you will need 1.5 megawatt of the power. So if you see your electric meter, okay, electric meter, how much load you have taken? You must be taken 5 kilowatt hour, 5 kilowatt load, or maybe 7 or 8 kilowatt, up to 10 kilowatt, not more than that. But if you want your vehicle to be charged within 2 minutes, you need 1.5 megawatt of the power. If you want that your vehicle should charge in 15 minutes, then the same calculation, 50 kilowatt hour divided by 50 by 60. 50 by 60, you will see it is 200 kilowatt or 0.2 megawatt. Now you can understand and you can see that how to, if your electric meter load is 5 kilowatt, then how much time you need in order to be within that limit, right? Otherwise there will be penalty and there are some other repercussion in your lines. Okay, so this is the one of the concerns that if you want to charge the vehicle quickly, you need lot of power. Now, why I have given this information and this particular data in a very simple way, that once the grid, right now what we are doing, we are using car in the India, maybe every year, maybe 50, 60 or 70,000. Or it is having some base load. Means all the time we suppose that the grid should give this much power. Okay, so the y-axis is the power, axis is the time. But in a typical day, if you see, say morning at 0 time. So this is at the left, it is the night 00 hour, and this is again full day over. So this is in between, it is the 12 noon. Now you see how a typical consumption or typical requirement of the power is there. You can see this plot. Okay, so it is going in the daytime during say 9 o'clock to maybe evening 7 o'clock. You need this much extra power. Okay, now once grid is working, so grid typically either it is hydro power or it is coal power, doesn't matter. It is designed for a particular power is very high. Then what happens? These demands, intermediate load and the peak load demands are met by some other sources. Okay, so those are the oil or gases. We have to use the oil and gases in order to meet that demand. So now you can understand, if everybody is charging his vehicle maybe after 10 years or after 5 years, there are millions of vehicles are there on the road, and everybody is charging in a charging station or somewhere. How we can see that during the morning time or night or morning there is no power, but if you see in the daytime you will have sufficient power. Okay, so this power, and this is the demand that we have, so this is known as a duck curve. So this demand, whatever extra energy we have with the solar, we can push it over here, and we may not require the additional oil and gas in order to satisfy the peak load requirement. Okay, but in the night time, what will happen? Again, you see the peak is increasing because now you are not having the solar. So that means during this time, if you don't have the stored energy, then you are supposed to, there will be lot of repercussion onto the grid. Okay, so the storage of the energy is one of the most important things, for not only for the load leveling, but for the CO2 and all those things. Because the solar power is available in the daytime, wind is available for a certain time, you are supposed to store that, and once there is a demand, you are supposed to utilize that stored energy. So here the role of the chemical engineer comes. So if you see electrochemical, all these devices that we know, which is either the battery or the electrolyzer or supercapacitor, these all are the electrochemical devices. These are used for the energy storage. And primarily the energy storage, if you are talking about, because the renewable energy is intermittent in nature, so you have to store the energy, and you have to, once there is a excess energy, you can store, and you can then discharge once you require it, so that you can maintain the grid, and you can at the same time you can save the CO2 getting into the environment. So there are different kind of energy storage are there: pumped hydro, compressed air energy, flywheel, and so on. But we will discuss more about the electrochemical systems. It will be the conventional batteries, lead acid battery, nickel cadmium, nickel metal hydride, lithium ion, or it can be the high temperature system, sodium sulfur, sodium nickel chloride, and so on, along with the flow battery, which I will discuss little bit more. So chemical engineer basically play a very significant role, because the batteries or the electrochemical batteries are nothing but the electrochemical reactor. We have a lot of experience on the chemical reactor. So if I tell you what is the difference between the chemical engineer and electrochemical engineer, chemical engineer basically talk about the three transport processes. Okay, mass, energy, and momentum, right? But the electrochemical engineer discuss one more transport, which is the charge transport. So chemical engineers are the right person who can understand the batteries in a better way. They can design, they have experience of the chlor-alkali plant where the chlorine gas, hydrogen gas generation is there, water electrolyzer to generate the hydrogen gas and the oxygen gas. refining, electroplating, all this experience the chemical engineers have. So based on that, if they work on these batteries and the electrochemical system, they can do wonders. So because we are talking about here this hydrogen generation, I just show one slide about because the India has given a national green hydrogen mission also. We are doing a lot of work in that national green hydrogen mission. For example, by 2030, India has committed that 60 to 100 gigawatt electrolyzer capacity will be generated in India, and at least 5 million metric ton of green hydrogen can be produced annually. If I am saying green hydrogen, that means you are electrolyzing the water with the help of the renewable energy. Once you are using the renewable energy in order to break the water into the hydrogen and oxygen gas, then that particular hydrogen is known as the green hydrogen. And we are also committing that we will have 125 gigawatt of the renewable energy capacity for green hydrogen generation and associated transmission networks. Now, we can store, as I have told, we can store the energy in the lead-acid battery, lithium-ion battery, or some other batteries, right? But here we are talking about the large-scale energy storage. Large-scale energy storage means we are talking about hundreds of kilowatt-hour to megawatt-hour electricity. Okay, so if I take a lithium-ion battery or the lead-acid battery, it is very difficult. It is not, the cost economics will not work. That you may understand maybe in the next slide. But here I just try to tell you what this flow battery are. So this particular system, this first system is the flow battery. So in this flow battery, you see, there is an electrochemical reactor. This is the electrochemical reactor, and we have the two tanks. One tank is known as the negative electrolyte tank, and the tank is the positive electrolyte tank. And we have the two pumps which are used to push this liquid or the electrolyte into this reactor, where a certain reaction takes place, and in turn you get the electricity, and whatever liquid which is coming from this, it is going again into the same tank. That means we are recirculating the liquid into the same tank. And the charging and the discharging is the same way. We can charge the battery with the help of the solar, wind energy, hydel, or the grid, whatsoever it is. We can always charge it from there. And for discharging, depending on the application, it can be discharged either to stabilize the grid. You can integrate with the grid. It can be used for the decentralized power or the rural electrification, or it can be used as a EV charging station. I'm not saying that it is used for the EV. It is used for making a charging station where this flow batteries are there. Energy is stored in this flow battery, and power and the energy. Decoupled power and the energy means this particular section, this reactor, that is responsible for the power. You see here. So schematically it is shown over here. So VRMP stack. So a lot of cells are there in series. Okay. So these cells will provide the once it is running. So this stack will provide the power, whereas the amount of the liquid in these two tanks will tell me how much is the energy. I will give you the analogy. The traditional car that you have an engine and you have the petrol tank. So engine is responsible for producing the power, and the petrol is basically carrying the energy, right? So if I want to tell you that you please increase the energy of your car, so what do you have to do? You have to store more petrol into the vehicle so that you can go for longer distance. In a similar way, if you can increase the size of these tanks where the active material is there, which is responsible for the reaction, then you can increase the energy without touching the power component. If you want to increase the power and you are not interested to increase the energy, you can also do that you can add up more cells in series so that you can get more power into the system. Okay, so decoupled power and the energy, deep discharge in the charge capability is one of the important feature. Then it is capable of 10,000 cycle, or you can say the life can be more than 20 years, right? And the chemistry, if you want to see, it is a very simple thing because we understand. So this particular battery is the vanadium redox flow battery. So vanadium exists in 4 oxidation state, +2, +3, +4 and +5. Okay, so this couple 2 and 3 we use at the negative side and 4 and 5 we use at the positive side. If you see the reaction V2 plus giving V3 plus an electron, similarly V5 is taking that electron and the proton from the electrolyte and gives the V4, and ultimately at standard condition you get 1.26 volt. Okay. So just a comparison, scaling up, if you want to scale up energy or power independently, in case of traditional battery, whatever battery you have to add. Okay, if you are adding in parallel, the voltage is same, capacity is increasing. If you are adding in series, the same set, the capacity is now same, the voltage is increasing. Whereas in this flow battery or the vanadium flow battery, if you want to increase the power, now you see, the power is increased. If you want to increase the energy, now you see this energy is increased. So that is the meaning of decoupling energy and power. Now this is the exploded view of a flow battery of a single cell. You can see this is the end plate. There are a lot of components are there like graphite plate, current collector, flow frame. Then this is the graphite felt electrode, which is on which the reaction happens, different gaskets, separator, and then again the similar set on the other side. So we are working on the electrode, membrane, electrolyte, bipolar plate, power electronic and scale-up studies. I'll just give a glimpse. So already I have taken 35 minutes, so in next 10 minutes I'll try to wind up by giving some glimpse of the work that we are doing. So some of the fundamental studies we have done, and we have been granted the patent also. We have published the work also. So here, because it is all the electrochemical reactions are a heterogeneous reaction. The reaction happens onto the surface. Okay. So what kind of surface we are using, that matters a lot. So here, what we have done, we have taken this is the graphite felt of one of the fibers I have shown. So in that fiber, what we have done, we have created some dents, okay, with the help of some thermal treatment. Now within that dent, we have, with the help of the solid state reaction, we have deposited the potassium. Okay, then we have taken out this potassium. So what we could get very high surface area, very high surface area. So the intercalation of the potassium was there. Then we have taken out that potassium. So we could get very high surface area. So this is the surface that you can see. Intermediate surfaces can also be seen. This is the graphite felt. This is the thermally treated graphite felt. This is the potassium treated, and this is the potassium along with the thermal treatment of the graphite felt. We have got very good result. You can see. So this particular plot shows the voltage versus the specific capacity for the KTGF that we have synthesized, that electrode. So that electrode, you see, the over potential is very low. At the same time, it is giving the very high specific capacitance. Similarly, if you see the cell voltage and the current density, the power, you can see, this is the power also. So around 350 milliwatt per centimeter square of the power we are getting with this particular electrode. And this is, if we quantify, it is 3 times more powerful electrode as compared to the graphite felt. Similarly, we have done, you see, the 2 components that we have discussed. One is the electrolyte, another is the stack. So the electrode is in the stack, electrolyte is outside. So electrolyte, that tanks that we have shown, generally people use the VuSO4. VuSO4 is very costly. So we have taken the V2O5 as a precursor, and we have designed a system or the equipment along with the process so that we could get the electrolyte where the precursor is V2O5. And the performance, you can see the performance of both the electrolytes taking VuSO4 as the precursor or the V2O5, which is very, very economical as compared to the VuSO4. This is 1/5 of the cost. So the performance is almost same. So this also we have filed the 2 patents, national and international. Indian patent we have been granted. Now the next question comes. So vanadium is the active species which is taking part in the reaction. So what is the source? If we can reduce the cost of the vanadiums. So what we could do, that we have used the spent vanadium catalyst. You see over here. If you remember the contact process for synthesizing or for making sulfuric acid, there we use the V2O5 catalyst, right? And V2O5 is a precursor that I have told for our case. So this is the catalyst, which is the spent catalyst we have taken from the sulfuric acid plant, and this particular catalyst is having only around 3 weight % of the V2O5. The rest is silica and different kind of metals. So we have to purify this V2O5. So we have used the Pourbaix diagram help, different kind of Pourbaix diagram. I'm just saying the basis. So from there, the catalyst that we have made in the powder form, from there we have done a lot of processes, and at the end we are getting the vanadium species which can be directly used in the electrolyte so that the battery can work. So we have published it in the Journal of Clinical Production. So the cost of the synthesis is very, very low, less than half of the cost of the industrial grade catalyst, industrial grade electrolyte. This I'll skip. We have also studied on the imbalance, how the imbalance is happening into the system. We understand once the liquid is going into one side, say negative side, and going into the positive side. So there is a separator or the membrane is there, which ideally should not allow the other, except the required ion, it should not allow the other species to migrate from one side to other side. But now no system is ideal. So what happens? There is a cross mixing is there, or mixing of one side electrolyte is going into the other side electrolyte, and that we have seen with the help of various experiments. One of the experiment we are showing how the volume is changing in the positive side and in the negative side. That you can see. The beauty was that the SOC of the system cannot tell us what is happening inside in this particular case. Okay. So the discharge capacity is reducing, but if you see the SOC is more or less constant in this particular zone. So we have done a lot of study. We have tried to understand that there is a particular point. We have segregated the negative side and positive side, SOC of the positive side, SOC of the negative side, which is very tough job. But we have tried that, and we could get that a particular inflection point come, and this inflection point is very, very important if you have to save the electrolyte in order to get degradation. So that point we have told that it is the ERP, electrolyte repair point, that repairing is well-known process. So we have based on the understanding, we have fabricated a device, and we have current we are drawing, what is the NF value, as the number of electron, and F is the Faraday constant. What is the flow rate? What is the surface area of the electrolyte? What is the volume of the electrolyte? Is a porous material. What is the resistance of the system? What is the activation? If we use all those parameters, if we use the Buckingham-Bai theorem, we could get 4 dimensionless numbers. These 2 dimensionless numbers are known to the scientific community, and these 2 numbers we have proposed to the chemical engineering community, and it is published in the Indian Chemical Engineering Journal. So these 2 numbers are the total charge utilization and the number of volume units. So the physical interpretation is also given over there, and we have tested it and we have verified our prediction with the other data. Now just at the end, I'll just show you some of the studies in the pictorial form. So this is a single cell. So single cell, we have started work around a couple of years before, from the single cell to the multi-cell, and this design was such that we should be able to, so there are 10 cells, and this is a 12-volt battery. So we should be able to analyze each and every cell which is inside, along with the flow distribution and pressure drop, everything. So we have done a lot of work, around 1 year of work we have done on this system. Then what we have done, and this is a bulky design, you can see, there are a lot of leakage points. All these points are the leakage points. These are the headers, and for every cell from the header, the liquid or the electrolyte is going into the stack. So this is the actual picture. Now thereafter, we have done the same thing in this kind of system, where you cannot see any liquid leakage points, and it is around 70% more compact. So this design, we have taken the concept from the plate and heat type heat exchanger. So with the help of the plate and heat type heat exchanger, all the header and the distribution of the liquid, how it is going, and how much is the pressure drop, those analysis have been done. So this is a 1 kilowatt system and 12-volt battery. Okay. So you can see how compact it is. So minimum leakage point, this is an industrial design and the suitable as a product. So we have, once we were scaling, so you see from a single cell, maybe a 10 centimeters square, we are going to more than 1000 centimeters square. Presently we are working on 1500 centimeters square. We have observed that once we are increasing the size of the electrode, there is a problem of the shunt current, and therefore the bipolar plate that we are using, there is a degradation. So we have tackled that, and we have done the study. We have done a lot of study in that in order to take care of the flow pattern, and that is responsible for the shunt current, and which is ultimately giving the degradation of the bipolar plate. So that we have tackled, and now you can see we are having no corrosion for a long testing time. Now at the end, maybe 1 or 2 more slides. We are also, because if we have to work for a product, we have to, apart from the chemical engineering, we have to go a little bit beyond that. So we are working on the power electronics. So we have designed the power electronics converter inverters for this particular battery, because these are not available in the market. These are new technologies, so it is not available. So initially we were using the lead acid battery power electronic, but we realized that is not good to use that, because it is not taking the full potential of the system. So therefore we have made our own power electronics, and right now we are developed, or in fact 2 kilowatt we have developed, till 5 kilowatt we are working. We have shown this technology at various fronts. So the Australian PM, Mr. Albanese, has come to IIT Delhi. He wanted to see the top 5 technologies of IIT Delhi. So our technology was one of station. So this is a charging station where the battery is here, and this charging station can be used to power to charge the mobile gadgets that the visitors are having, their mobile, their power bank, their their laptop, whatever they wish, they can charge. So this is kept just below the main building of IIT Delhi. And thereafter, we are also working on a 2 kilowatt system, the charging station that we are developing in IIT Delhi, so that we can store the energy in the flow batteries, and we can use that stored energy to charge the 2-wheeler and 3-wheeler which are plying in the campus. So that is almost ready. So by next month we are going to deploy our system over there. Our group has also received the first prize under the DST's National Innovation Challenge Award. Out of the 76 applicants, our group was the winner. Now we are working on 5 kilowatt, 10 kilowatt hour VRFB system, and it is to be deployed in IIT Delhi. So it is funded by one of the industry. So they have given a fund of around 75 lakh rupees to make 2 systems for them and deploy on the real ground. So that is within a month or 2, we will deploy that also. We are also having a startup. Its name is IICHE Technologies Private Limited. So we are delivering such kind of system or any kind of system, electrochemical system that you need. Our team is capable to deliver. So we have delivered to various IITs, ISCs, industries, and not only the flow battery, fuel cell, flow battery, all kind of electrochemical system we are having good understanding. Therefore, we are able to supply. And it is all the work that I have shown for this particular domain related to flow battery. It is funded by different organizations, private and industrial also, like Synovus Energy, then Rokaya, then some other work is also included over there. So like ISRO, then Saturnus, US, Synovus Canada, DST, DBT, Ministry of Education, CSIR, Oil India, DBT, all these, LG. So these are the funders. Along with that, my team, all the students have worked a lot and they are working still to realize whatever we are doing in the lab in a product form. So with that, I would like to thank everybody. And this is the email ID of our company. In case if you need related to the electrochemical system, we will be happy to help you. So if you have any query, you can ask. I'll just try to switch on the camera as well. So I don't think there is any.
Another is the downstream processing. So upstream processing is associated with the production stream, and the downstream processing is associated with the isolation, purification, and recovery of the product. So purification and characterization of the antibiotic is the last step. Then methodology is adopted. Now, first we have used one of the statistical method, that is COVT. COVT is change of one variable at a time. One variable is kept constant and other 3 variables, the other 3 variables are changed. Other 3 variables